All right, welcome back. We're going to continue this journey of taking antiderivatives by talking about how to take antiderivatives of other functions. We saw in the examples that were completed that there's this property that can be used for antiderivatives, where if we take the antiderivative of a constant multiplied by a function, that constant can be factored up front. So here it is listed more formally. We also saw this property, that the antiderivative of two functions added together is the sum of the antiderivatives. And we finally use this property, that the antiderivative of x raised to a power is equal to x raised to that power plus 1 divided by that power plus 1. I wrote it differently. I wrote it as 1 over n plus 1 in front, but it's really the same thing. Dividing by 2 is the same thing as multiplying by a half. Dividing by 7 is the same as multiplying by 1 over 7. I wrote it down, I didn't mention, that this formula, this anti-power rule, works for all powers except negative 1. Look at what happens if the power is negative 1. In the denominator, you would have a division by 0. So something special happens. And here it is. Here's the special thing that happens. If you take the antiderivative of x raised to the power of negative 1, which is the same thing as the antiderivative of 1 over x, you get ln absolute value of x. We're going to talk more about absolute value functions. This is often simplified to ln of x plus c. So dropping the absolute values. The most general answer, the one that is correct, contains the absolute values. Another antiderivative formula is really simple. Well, since the derivative of e to the x is e to the x, then the antiderivative of e to the x is also going to be e to the x plus c. And then the last one, that's kind of part of the simplest class of antiderivatives, is the antiderivative of an exponential function that has a different base. So what if it's not base e? What if it's base 3 or base 4? So the general antiderivative of a to the x, where a is constant, is a to the x divided by the ln of a. I'm going to write down some alternatives. We could say or 1 over n plus 1 x to the n plus 1 plus c. And for this one we can say or 1 over the ln of a times a to the x plus c. That second form might look a little bit better. When you take the derivative of a to the x, you get a to the x multiplied by the ln of a, keeping in mind that ln of a is a constant. So you get a ln of a on top, ln of a on the bottom, they're going to cancel. That's why this works. That's why you need the ln of a in the denominator to cancel the ln of a that comes out when you take the derivative, and that ln of a will appear in the numerator. It's a good question. If we had questions right now, why is there an absolute value there for that ln? And I'm going to wait until we talk about pictures, the visual meaning, visual interpretation of antiderivatives to answer that question. So those are the basic ones. What are the less basic? The worst part about memorizing derivatives is memorizing the derivatives of the trig functions. And the worst part so far, the day is young, of memorizing or learning the formulas for antiderivatives is the antiderivatives of the trig functions. Fortunately, if you know one, you know the other one. Because the derivative of cosine of x is negative sine of x, it must be the case that the antiderivative of sine of x is negative cosine. Since the derivative of sine of x is cosine of x, it means that the antiderivative of cos must be positive sine. And then we can do similar things. We know the derivative of what the derivative of tan of x is, secant squared. So the antiderivative of secant squared must be tan. Antiderivative of cosecant squared must be negative cotan, because the derivative of cotan is negative cosecant squared. See how it works? We're answering the question backwards. What do you take the derivative of in order to get this? Sometimes we need to attach an extra minus sign to it to take care of the minus that will come out when we take the derivative. The derivative of secant is sec x tan x, so the antiderivative of sec x tan x is secant. And it's the same for the cosecant cotan. What we're going to skip in this course is none of that. We're not going to skip any of this, but we are going to skip the inverse trig functions. We haven't talked about them. We didn't talk about arc sine, arc cosine, arc tan, or the other ones, the other three. They are in almost all calculus textbooks, and they're in almost every calculus resource that you can find. They're really neat, but they're not part of the course. I mentioned that this is kind of a scary looking list of things to memorize. But it really is no different than memorizing the derivatives of the trig functions. Once you memorize one list, the other one's free. That said, despite not being any extra expense to memorize both lists, if you have an opportunity just to write down the formula and have it in front of you, that's the most efficient thing. That's the fastest way and the least error-prone method. Have it on paper, have it in front of you. So I'm going to go ahead and use those derivative rules that are here, the trig antiderivative rules, and the 1 over x and e to the x antiderivative rules, and I'll solve an initial value problem or boundary value problem. We're given the derivative of the mystery function and asked for the mystery function. So to go from the derivative to the function, we're going to take the antiderivative. We'll get a plus c, and that plus c will pin down the exact value using f of 0 is equal to 2. Okay, so we're taking the antiderivative of the first term of e to the t with respect to t, not any different than the antiderivative of e to the x with respect to x. We're just using a different letter of the alphabet, plus 2 times the antiderivative of t with respect to t, plus the antiderivative of 2 with respect to t. And I'm purposefully not writing it as 2 times 1 because I think it weirds everyone out. All right, now if you flip back a few pages, you'll see that the antiderivative of e to the x is e to the x, and the antiderivative of e to the t is e to the t. Antiderivative of t with respect to t is 1/2 t squared. And the antiderivative of 2 with respect to t is 2 times t. And we get a big global plus c that comes from the 3 contributions, the plus c from each of those 3 parts. Okay, so let's simplify e to the t plus t squared plus 2t plus c. Now we are going to say that f of 0 is equal to 2. So 2 is equal to e to the 0 plus 0 squared plus 2 times 0 plus c, and we'll simplify. 2 is equal to, anything to the 0 is 1, so 1, whoa, very good, 1. 1 plus 0 times 0 is 0, 2 times 0 is 0. So 2 is equal to 1 plus c. That means c is equal to 1. And we can make a conclusion, thus, f of t is e to the t plus t squared plus 2t plus 1. And you can imagine an alternative question. What is f of 3? Right? Okay, another example, this time with trigonometry. We're told that the derivative of the mystery function is 3x squared plus the cosine of x. and we're given some information about the value of the mystery function at x equals 0. We're told that its y value is 2. So I'm going to write down the general antiderivative. F of x is the antiderivative of f prime. We take the antiderivative of the derivative to get the original function. Antiderivative of 3 times x squared with respect to x plus the antiderivative of cosine of x with respect to x. Don't get confused about the difference between derivatives and antiderivatives. This question is asking d by dx of what is equal to cosine of x. So what do you take the derivative of in order to get cosine? And the answer is sine. Plus c. So we get 3 times 1 over 3 x cubed plus the sine of x, and then a big plus c. We can simplify x cubed plus the sine of x plus c. Now we're going to use our information. What is f of 0? F of 0 is equal to 2. So 2 is equal to 0 cubed plus the sine of 0 plus c. So 2 is equal to 0 plus sine of 0, sine of an angle that's pointed straight to the right. So I think about that tiny triangle. When you shrink that angle down to nothing, the opposite in that triangle is going to be very short. It's going to be 0 high, and sine is opposite over hypotenuse. So you're going to have 0 divided by whatever that hypotenuse is, which is 0, plus c, and that means that c is equal to 2. And we can make our conclusion. Thus, f of x is equal to x cubed plus the sine of x plus 2. Okay. Another example. This one, test style. We're asked to find f of pi. What is the value of the function evaluated at pi if the mystery function's derivative is given by what's there? So I'm going to start by taking the antiderivative of the derivative to get the original function with the plus c. So the antiderivative of secant squared of x plus the antiderivative of sine of x. So antiderivative of secant squared is tan. Derivative of tan of x is secant squared. Antiderivative of sine is negative cosine. And we get a plus c. Next, we will plug in x equals 0 and use f of 0 is equal to negative 1 to pin down the value of c. So f of 0 is equal to negative 1. We're going to have negative 1 is equal to tan of 0 minus cosine of 0 plus c. So negative 1 is equal to, what's tan of 0? You can do the same thing. If you don't have it memorized, think about opposite and adjacents. If our angle is almost 0, that's what our triangle looks like. It has a very small opposite. And the adjacent and the hypotenuse are almost the same length. Tan of 0 is opposite over adjacent, so 0 divided by whatever the adjacent is, which is 0. Cosine of 0 is adjacent over hypotenuse. And if the adjacent and hypotenuse are the same length, we're going to have, let's say, 5 divided by 5 or 7 divided by 7, which is 1. Cos of 0 is 1. Remember, plus c. We're going to add 1 to both sides, so c is equal to 0. And we can make our statement, our second last statement for the question, that f of x is equal to tan of x minus cosine of x plus 0. Now, what is f of pi? F of pi is equal to tan of pi minus cosine of pi. So I'll draw another little quick picture. What's tan of pi? Pi is 180 degrees, so we're out over here. In that direction, the opposite is positive, but getting small. The adjacent, which is in the x direction, is negative. We're on the negative x side. We're on the negative x part of the number line. And the opposite's going to 0. So tan, opposite over adjacent, we're going to have 0 divided by a negative something, 0 over negative 7, which is 0. Cosine of pi, we have a negative, let's say negative 7 divided by 7. Since the hypotenuse and the adjacent are going to be the same magnitude, but in this case, over at pi, over 180 degrees, over in that quadrant, the adjacent is negative. So same magnitude, but negative 7 over 7, negative 10 over 10, whatever it is, it's going to be negative 1. So subtract negative 1, and our answer is positive 1. Okay, some more standard types of examples. So straightforward antiderivatives. No finding constants or anything. How do you take the antiderivative of a sum of a bunch of terms? Well, you split it up into a sum of integrals, a sum of antiderivatives, and use the appropriate rule for each part. So I'll do this: x to the power 5 antiderivative, cos of x antiderivative, 7 antiderivative, and sec x tan x. And if you have your formulas in front of you, it's not so bad. The derivative of secant of x is sec x tan x, so this is just a secant of x. I might as well put the plus c in. The derivative of sine is positive cosine, so this is going to be positive sine of x. And the other parts are the anti-power rule, 1 over 6 x to the power of 6 and 7x. That's it. Don't do weird stuff. All right, about the next one. This one requires a little bit more work. When we split it up, we also have to use an exponent law. Antiderivative of 1 with respect to x plus antiderivative of e to the x with respect to x, and then minus 5 times the antiderivative of x to the power of negative 1 with respect to x. And that's that last thing, that's a special case. Special case for n equals negative 1. It's not the anti-power rule. Antiderivative of 1 is x. Antiderivative of e to the x is e to the x. And then the antiderivative of x to the power of negative 1 is the ln absolute value of x plus c. And that's it. Okay, trickery. Trickery abounds everywhere. We had some problems already in an earlier video where we had to split the expression up using fraction rules. So we're going to have to do the same thing here. So I'm going to split this as the integral antiderivative of tan of x over tan of x plus the antiderivative of sine of x over tan of x. Tan over tan cancels. We just have antiderivative of 1. So that's going to be nice. That's just x. We'll get a plus c at the end. The second part, we're going to have some problems. There's a few ways that we can proceed. what is tan of x? We learned that tan of x is opposite over adjacent. We learned that sine of x is opposite over hypotenuse, and cosine of x is adjacent over hypotenuse. And somewhere in there, I'm pretty sure it was mentioned, but if not, it's okay, I'll mention it here, that tan of x is sine of x over cosine of x. I think it was mentioned in the evaluations. If you know what sine of 0 is, and you know what cosine of 0 is, you can find tan of 0. Because tan is sine over cos. So, sine of x over tan of x is sine of x divided by sine of x over cosine of x. We can change the division into multiplication by the reciprocal. So sine of x multiplied by cosine of x over sine of x. And those signs will cancel, and we just get cosine of x. I still have an integral symbol there, I'm going to have to write it. Integral of cosine of x. Okay, antiderivative of cosine is negative, positive, I'm thinking positive sine of x. That's our answer. Okay, the next one, we're going to do the exact same type of thing. We're going to split it out. We have an integral of e to the 2x over e to the x with respect to x plus 2 integral of e to the x over e to the x with respect to x. What is e to the 2x over e to the x? This is e to the 2x minus x, which is e to the 1x. What happened there was we used an exponent law. B to the m over b to the n is b to the m minus n. Subtract the exponents as long as the bases are the same. Our base happens to be e. It looks weird, but it's no different than any other base. So I'm going to simplify that. Integral of e to the x dx plus 2 times the integral of 1 with respect to x. Okay, antiderivative of e to the x is just e to the x. Antiderivative of 1 is just x, so we have 2 times x there, and we get a big plus c from both pieces, which we can combine into 1 plus c. That's our answer. All right, let's kick it up a notch. Same trick, right? These are all the same strategy. It's do what you can to use the rules that you have. Recycle your methodologies. Find a way to force fit your problem so that it's possible to use a strategy that you've already validated. This is super general. It's like it looks like the only thing you're learning about is calculus and taking antiderivatives, but there's a hidden curriculum that's hidden across mathematics courses. It's about problem solving. It's about recycling whenever you can, taking a methodology from one problem and seeing if you can use it on a different problem. It's why math has become very powerful as a tool, because you can recycle almost all of it. Okay, so the first 2x cubed over x squared with respect to x, antiderivative of x squared secant squared of x over x squared with respect to x plus antiderivative of x over x squared with respect to x. Now I've used it a few times. I should write down the rule again, using just a fraction rule that has nothing to do with calculus, nothing to do with antiderivatives. A plus b plus c over d is equal to a over d plus b over d plus c over d. I should mention that if it was flipped, if it was one thing on top divided by 3 things on the bottom, you can't split that up. That is a different beast. We'd be in big trouble if we have one of those. At least big trouble if all we have is what we've already learned. Okay, now we're going to simplify each of these pieces. We have 2 antiderivative of x. X squareds cancel, antiderivative of secant squared of x. And then antiderivative of 1 over x. Or if you want, you can rewrite that as x to the power of -1. Antiderivative of x is 1/2 x squared. Antiderivative of secant squared is tan. And then antiderivative of 1 over x, that's our special case, our x to the power of -1 case. We can't use the anti-power rule. This is where the ln absolute value of x comes in. And we get a big plus c. And I guess the only thing we can do is simplify the 2 times 1/2. So it becomes x squared plus tan of x plus ln absolute value of x plus c. And I mentioned the first time, I didn't mention it the subsequent time it came up, but sometimes we get lazy. Or have good reasons, like a domain reason. Maybe our x domain is only positive x value, so it doesn't matter its absolute value of x. Okay. Second example of a problem where we are given f double prime and given 2 pieces of information about one piece about f prime at 1, another piece about f of 1, and we're asked to find the original function. So step 1, integrate f double prime of x to get f prime. And use f prime of 1 equals 10 to find c. So we'll do that. F prime of x is the antiderivative of f double prime of x, which is the antiderivative of x to the power of -2 plus 6 times the antiderivative of x, each with respect to the x variable. We're going to use the anti-power rule in the first one. We'll have negative, I'll do it properly, 1 over -1 times x to the power of -1. And then the second piece, we have 6 times 1/2 x to the power of 2. We get a plus c. So -1 over x plus 3x squared plus c. Now we're going to use our information. So f of -1, f of positive 1 rather, f prime of positive 1 is equal to 10. So we have 10 is equal to -1 plus 3 plus c. So c is equal to 8. So now we have what f prime is. We have that pinned down. Is -1 over x plus 3x squared plus 8. Now we're going to do step 2. Integrate f prime of x to get f of x and use f of 1 is equal to 2 to get the other c. So f of x is the antiderivative of -1 over x plus the antiderivative 3 times the antiderivative of x squared with respect to x plus the antiderivative of 8 with respect to x, or if you want 8 times the antiderivative of 1, up to you. we have negative ln absolute value of x. For the second piece, we'll have 3 times 1/3 x to the 3. The 3 and the 1/3 will cancel. I'm just skipping that step because I'm running out of space. X to the power of 3. And then 8x plus a c. Now we use our information. We use f of 1 is equal to 2. So we have 2 is equal to negative ln absolute value of 1 plus 1 plus 8 plus c. So 2 is equal to 0, ln of 1 is 0, plus 9 plus c. That means c is negative 7. And we can conclude what our function is, what our particular solution is. F of x is equal to negative ln absolute value of x plus x cubed plus 8x plus c. Okay. Okay, very similar problem. Find f of 1 given this information about f double prime. So we're going to do the exact same procedure. We're going to step 1 find f prime of x and use f prime of 2 is equal to 3. So f prime of x is equal to 8 times the antiderivative of x to the power of negative 3 plus 6 times the antiderivative of x to the positive 2. So power increases by 1. We have 8 times 1 over negative 2 x to the power of negative 2 plus 6 times 1/3 x to the power of 3 plus c, which we can simplify as negative 4 x negative 4 over x squared. I'll do that right away. Bring that power back down. Plus 2x to the 3 plus c. Now we'll use our information. F prime of 2 is equal to 3. So we'll have 3 is equal to negative 4 over 2 squared plus 2 times 2 cubed plus c. So 3 is equal to negative 1 plus 16 plus c. So we'll have 15 and subtract 15 from both sides. So c is equal to negative 12. Please report if I make mistakes. This is exactly where mistakes will be made. So we can make a temporary partial conclusion that f prime of x is negative 4x to the power of negative 2 plus 2x cubed minus 12. Now we'll take the antiderivative of that. So step 2, find f of x and use f of 2 is equal to 5. Okay, so f of x is going to be negative 4 times the antiderivative of x to the power of negative 2 plus 2 antiderivative of x to the positive 3 minus antiderivative of 12. And I almost forgot my dx's. Okay. So we use the anti-power rule for each piece. We're going to have minus 4 times 1 over negative 1, x to the negative 1, plus 2 times 1 over 4 x to the 4 minus 12x plus c. Now we'll use information. We'll use f of 2 is equal to 5. So we have 5 equals 4 times 1 over 2 plus 1/2 times 2 to the 4 minus 12 times 2 plus c. So what I did a few steps in one. I took the 2 times 1 over 4, made it 1/2. Simplifying that, took the first piece, negative 4 divided by negative 1 is positive 4. And then I changed the x to the power of negative 1 to 1 over x and plugged the 2 in. So lots of steps there. Let me know if you've had trouble with any of that when you're going through this. Then simplify each of these. So 2, and then 2 to the power of 4, 16 over 2, 8, minus 24 plus c. So we have 5 equals negative 14 plus c. So c is equal to 19. And we're almost done. This is the second last step. Thus, f of x is equal to 4 over x plus 1 over 4 x to the 4 minus 12x plus 19. We want f of 1. So f of 1 is 4 plus 1 over 4 minus 12 plus 19, which isn't as nice as I thought it would be, but we'll have to just make do. Negative 12 plus 19, so 7, so 11. We'll double check that. 11 plus 1 over 4. Make common denominators, so 44 over 4, so 45 over 4. Sorry about that. Didn't do the question ahead of time. Just imagine the answer would be nice. Not very nice. But the answer should be nice for something like this. You should get like 3 if the question has been cooked properly. Now that is the end of the material for the week. What I want to do is just motivate what's coming next. We saw how to take the antiderivative of expressions that come from derivatives of functions that can be completed with a power rule, derivatives of functions that can be completed using the exponential derivative rule, derivatives of simple log functions like 1 over x, and then all the trig functions. What makes all those easy to access is that the derivative rules are simple. They're one thing, one rule that you have to use. You may have to manipulate the expression to make it fit the rule, but there's only one thing you have to do. To make it more complicated, well, how do we, for example, solve this problem? The derivative of the mystery function is 8 times e to the 2x. What do we take the derivative of to get that? So we can try a few things. Propose, make a proposal. Propose f of x equals, let's go just e to the 2x. And then check. So f prime of x is e to the w times w prime. So e to the 2x times 2, which is wrong. It's not 8 e to the 2x. How do we fix it? So what if I put an 8 in front? Maybe the 8 will fix it, right? Another proposal. Propose f of x. So that was too small. Now we'll do 8. 8 e to the 2x. Let's see. So f prime of x is 8 e to the w times w prime. So 8 e to the 2x times 2, which is 16 times e to the 2x, which is too big. It's wrong. So one of the bowls of porridge is too hot, one of them is too cold. There's got to be one that's just right. What do I need to have in front to get the 8? So what do I need in front of the function? It's something. A times e to the 2x. What does that little a have to be? What's necessary to put there so that the derivative is an 8 in front? What if we try a 4? And we'll check. We'll confirm. Take the derivative. We'll get 4 e to the w times w prime. So 4 e to the 2x times 2, which is 8 e to the 2x as needed. So I'm going to put down the answer. Thus, f of x equals 4 e to the 2x plus c. Okay, similar reasoning. How do we do this one? E to the 7x. If I take the derivative of e to the 7x, so let's say I make that my proposal. I propose f of x equals e to the 7x, and then I take the derivative. F prime of x is going to be e to the 7x times 7, e to the w times w prime, which is 7 e to the 7x. I don't want the 7 there. The challenge does not have it. The puzzle doesn't have a 7. So what do I need in front to cancel the 7 that will come down? Well, I need a 1 over 7. How about the next one? What if I don't know what a and b are? What if we just leave them in general, leave them as parameters? What do I take the derivative of in order to get e to the ax plus b? So we could try make a proposal, right? Make a proposal just like we did the other ones and see what's wrong with our proposal and fix it. So propose f of x is equal to e to the ax plus b. Just maybe that's it. Now we'll take the derivative. F prime of x is e to the w times w prime. So e to the ax plus b times the derivative of ax plus b, the derivative of a times x. So the derivative of 5x, the derivative of 3x, the derivative of 2x is just going to be 3 or 5 or 2, whatever that constant is. So a, and the derivative of the constant b is 0. So I'm going to have a times e to the ax plus b. I'm off by an extra a in front that I don't want. So what do? I put a 1 over a. Probably looking at that box, wondering what goes in that box. Something good goes in the box, right? No, something bad goes in the box. I'll show you. Thus, f of x is equal to 1 over a times e to the ax plus b plus a constant integration. What I have to put in the box is a warning. That if f prime of x equals, let's say, e to the x squared, then f of x is not equal to, so we take the derivative, we get e to the x squared multiplied by the derivative of x squared, so e to the x squared multiplied by 2x. So you think, oh, I'll just divide by 2x, right? It's not. 1 over 2x times e to the x squared plus c. Why? Check it. Test it out. We need a quotient rule, and we will definitely not get e to the x squared back. So you have to be very careful with this logic. You can't just propose something, take its derivative, and figure out what you need to add in to fix it, because sometimes it's more complicated than that. And actually, the example that's there in the top right in green is impossible to solve, at least in terms of elementary functions. That's another thing we'll learn about inside this section that we're continuing on integration, that unlike derivatives, if I give you a function, it doesn't matter how nasty it is, if you have enough time, enough paper, enough pencils, you can take its derivative. If I give you the reverse, if I give you the derivative and ask you what is the function, it's very easy to give you one that's impossible to solve. It doesn't matter how long you have, how much paper, doesn't matter anything, you just can't do it. It is not a problem that can be posed in terms of elementary functions. Anyways, we'll pick up on this idea of how to do more general antiderivatives and a systematic strategy for doing this carefully, and it hinges on this dx thing that I almost forgot to write in one of the examples. It hinges on that dx thing and playing around with that. See you next time.